All right, so you're all here, I guess, for 819, which is the homotopy type theory. So that's good, I hope. If you're not, then it's time to switch rooms. So what I want to do is today I want to organize a little bit, to say a little bit about what we're probably going to be doing and a little bit of an overview and background. And I also need to get some sense of who you all are and what you want to do, like how we want to run the course. So the big thing is this. So if you look, I set up a course web page, which is at, Twiddle RWH. Course is hot, so you can have a look at that. Maybe some of you have looked at it. And there's a brief synopsis there, which you can look at, which is like 3-4 paragraphs, so you can just get an idea. And there's the beginnings of a schedule. The schedule that I'm going to follow during the semester is going to be determined dynamically. I don't really know exactly what the order of lectures is going to be. It partly depends on you, partly depends on lots of other things. So I'll say in a second why. So I'm going to fill this in as the semester goes along. And in particular, what I'm going to do is populate that with notes. So there will be some notes that go along here that are going to be prepared by you. So here's the thing. Okay, so this is the main thing that I want to do. So I view this as a graduate research seminar, and so I'm not like in the business of trying to test you and chase after you and make sure you know stuff and give you a grade. Okay, so that's what we're not doing in the class like 819. On the other hand, I want to make sure that everyone there are two provisos to that. One is that there are some number of undergraduates in here, right? How many undergrads? Like 1 or 2 or 3? Okay, not so many, but that's a special case. I have to deal with the undergrads. But setting that aside, that's my plan. But I want to make sure that you guys stay engaged throughout the semester. So I'm going to ask you to work on preparing notes. So the way that I propose this to work is the following, is I want you to sort of pair up and send me mail. Send me email, I'm RWH at CS, and send me an email about what the pairs are. And the reason what I want you to do is I want to have 1 pair per week. It seems to work best with pairs. It's sort of like pair programming, and it helps with the workload. So it's 1 pair per week, and it'll be one set of course notes per week. And there's one thing that I want to say. I was thinking. And so there are 2 things I want to say about this that are very important. One is that time is of the essence, as they say. So it must come out immediately within 1 week. We can't have you preparing week 1 homework 5 weeks later. It defeats the purpose. Okay? So that's the first thing, is that these things have to be timely. So doing pairs, I think, is going to help do that. And the second thing is, and then I really need to say this, I know from experience, what you're not doing is stenography, okay? I do not want, I'm not doing this as an exercise in ego gratification where you write down every little word I say and every joke I make and every mistake I make. You're not a court stenographer. Okay, so that's important. So writing the set of course notes that is appropriate for that week is a somewhat creative exercise, meaning that you have to digest what the main topics were that we discussed this week and put them in a sensible form. Okay, between the 2 of you, whoever the 2 of you are. Okay, I've had in the past it's kind of broken down because what I get is pretty much a tape recording, a line by line of everything it said with no interpretation or organization or correction or background or filling in exercises or anything. And that's not so useful for everybody else, and it's not so useful for you. Okay, so this is the thing I really want to say. And then what I will do is Favonia and I I should say, introduce Favonia. So Favonia's over there. Favonia volunteered to serve as a TA. This is purely altruistic because he doesn't get any credit for doing this because it's a grad seminar. So Favonia and I will review and correct before we put them out on the web page to make sure. So, and you will sign them, right? They will be yours, okay? So you will sign them. So you will author them. So your name will be on them, and once they go out on the web, that's it. It's permanent. So this is on your permanent record. So you're going to take some pride in what you're doing. That's what I want you to do. Okay. So I don't want you to be the court stenographer who nobody knows who that person is, and all they do is write down every and 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 stuff. That's not what we need. Okay. All right. So that's the idea. Okay, so this is the main thing about the workload, and we're also going to have, so that's one thing, is a sort of note-taking. And the second thing is homework assignments, and these will be sort of sporadic. And we may or may not, it depends on how things flow, we may or may not do stuff with proof assistance, but I'm mainly interested in developing the underpinnings of homotopy type theory, because I'll say something about that in a minute. And so Favonia will check these. We'll check these, and for those of you like the undergrads who I have to assign a grade to, then we're going to have to be quite rigorous about this. Okay. For the rest of you, I would say it's this I'm going to make both of these things mandatory, but I want you to keep up with this, even though I'm not going to be like at the end assigning you a grade, okay, or that means anything. I'm not going to try to give you like an A or B or a C, okay. So we're all in this because we're interested in it only, okay. So that's the idea. Okay, so Favonia will check those homework assignments and will work with you if you have any difficulties. So it's a tool, really, it's a tool for you to use, and I'll assign them and we'll check them, and that's my current plan, what we're going to do. And as I mentioned, these are primarily, I intend primarily these to be written, but maybe we'll do some hacking. And then I wanted to say a little bit about that. And what I want to avoid in this course is the well-known sort of video game aspect of using proof checkers, which is managing to get the thing to say okay and get to level 7 without really actually knowing what you did. Okay, and that's very possible to do. Okay, there's a lot of things you can do where you just like work your way through and whatever, and then you get the thing done and the hell with it. Okay, and that's not really the kind of level of understanding I'm hoping to convey in the semester. So I'm going to consider that kind of aspect if we're going to do some hacking around, which is a lot of fun and is part of the motivation of what we're doing, but I'm going to consider that somewhat secondary, okay, because I want to downplay that aspect of it, but that's what I think will happen. Okay, so that's like the structure that I propose. If you don't agree with this structure, you're welcome to send me mail and we can organize it. It really depends on you and what your commitment, what you want to be doing. But I think it seemed like this was a reasonable first cut at a way of keeping everyone engaged and involved in the course, so that the cooperation, so that the participation is meaningful and it's not just me like droning on for all semester long about some random thing. Okay, so that's it. Okay. So believe it or not, there's a textbook for this course. So this is very unusual for a course like this, because typically a course like this is like whoever's up here is just making it up as they go along. And I kind of am sort of making it up as I go along. But we happen to have prepared last spring in an enormous hurry this textbook, which turned into 600 pages approximately on the subject, which we will sort of follow. Somewhat follow. Well, you can. I'm not going to like start on page 1 and let's like work our way through, but we'll certainly draw a lot of things that are in here. I don't think, depending on your background in type theory and such things, I'm not sure how accessible the book really is. Okay, I'm too close to it to know. I'm not really positive, but I don't think you can really learn, I'm pretty sure you can't really learn type theory from scratch if you never heard about type theory before. By starting on page 1 of that book, it's probably not going to work. Okay, what it really is if you more or less know type theory, it's then an amplification of a number of ideas in type theory, which I'm going to explain a little bit more. And half of the book sort of develops somewhere. There's like part 1 and part 2, I think. Yeah. So part 1 is just like called Foundations applications, which is just like the type theory that's going on, and then part two is a whole bunch of applications of homotopy type theory to various subjects, including, in particular, homotopy theory. But as a discussion that, as a point I'm going to make clear in a minute, although it's called homotopy type theory because of its motivations come from homotopy theory, and I'll explain what all that means at some point, it really is a self-standing subject. It's not really tied to algebraic topology. What it really is a somewhat sophisticated analysis of the concept of equality in constructive type theory. That's it. Okay, that's what the whole subject is. Okay, so what I'm going to do is, in order to make that statement hopefully meaningful for you, what I'm going to do today is I'm going to give a slight bit of background about the subject of type theory and where that comes from and what are going to be the relevant points. And then I'm going to start out with some ultra basic things that I'm kind of hoping that everyone knows, but it will help me fix terminology and ideas, and also it will help people who maybe don't have necessarily a lot of background in type theory. Okay, so what are we doing? So the foundation of what we're doing is a subject that is normally called intuitionistic type theory. And giving it a name like this, I mean, and there's an unfortunate notational clash that's going to come up. So let me just call TT for this. Okay, I would call it ITT, but you'll see why in a minute why that's usually not what people do. Okay, which is primarily, but not exclusively, based on the work of the Swedish logician Per Martinlöf. Some of you may know this, who's been developing the subject since the early 1970s, so I don't know, let's say around about 40 years now, something along those lines. And based on, primarily you can look at it as an analysis and expansion of Brouwer's, the Dutch mathematician Brouwer's program of what he called intuitionism. Now, I'm going to say a little bit about this, but I'm not trying to run a course on philosophy of mathematics, so I don't want to get into a long discussion about these issues, but I'll explain to you, I want to explain to you the starting points so that you can get an idea, okay, so that you can get an idea of what this means. I'm going to say something here, okay, but just to give you your bearing. So what happens is that there's a base notion of type theory which has evolved over time. There's no one thing you can point to that is type theory, because things have evolved and ideas have been developed over 40 years, as you could well imagine. But they're pretty settled by now. People have a pretty good idea. So there's a base type theory. And then there are different variations on it which we're going to consider. So there's something called ITT, which is the core theory that we'll discuss. And that's called the intensional type theory. So the terminology is intensional type theory. So I could have called intuitionistic type theory ITT, then this would be IITT, but anyway, the convention that everyone uses is ITT means intensional type theory. And this is going to be, for our semester, is going to be a starting point, and I'll explain to you very shortly what we're going to do. This is the basis of what we're doing. So the starting point will be something called intensional type theory. And the reason it's a nice starting point is that various other forms of type theory can be seen as elaborations of or extensions of ITT. So in particular, there's another type theory called ETT, which stands for extensional type theory. And the word intensional, by the way, and extensional especially, is grossly overused in type theory. And it often means lots of slightly similar sounding things that are not technically related to one another. So you have to be really careful when people start talking about extensional. So what happens is we can think of this as satisfying an equation in the sense that you can think of it as the core intensional type theory plus some additional principles which are going to be called equality reflection and what's called uniqueness of identity proofs. And I'll say I'll give you a hint about what these mean in a little bit later. So to write this down, this is called equality reflection right now that this is not going to mean a lot to you, but I'm just trying to, I like to do iterative deepening. So this is something called equality reflection. This is called uniqueness of identity proofs. And in retrospect, in a technical sense that I'm of identity proofs, and in retrospect, in a technical sense that I will make precise a little bit later, one could really say what this is the intuitionistic, let me write that, theory of sets. And in fact, you could even say that the extensional type theories like Newpearl are actually a kind of constructive set theory. And it's inspired strongly by the work of Bishop, who developed analysis on a constructive foundation, and his notion of set is quite related to the idea of set that arises in ETT. So I'll get back to explaining what these things mean. So what is hot then? Homotopy type theory is actually a different elaboration of ITT plus some other things. So let me continue my pattern. So this is called homotopy type theory. Homotopy type theory. And it's an elaboration of intuitionistic type theory with two other axioms that are incompatible with ETT. These are like different directions in some way. Have two things, what are called higher inductive types, which we'll explain. So that stands for higher inductive types. And I'll tend to use the word higher a lot, and we'll see later what I mean by that. Plus an axiom called the univalence axiom. That's what hot currently means anyway. And maybe in a year's time, or who knows, we might mean something slightly different by hot, but that's the gist of it, okay? And the idea here is if ETT is an intuitionistic theory of sets, then what hot is it's a kind of intuitionistic theory of what are called, scarily enough, weak infinity groupoids. Uh-oh. All right, this sounds bad, okay? But it's actually not that. It's not like such a big deal, and I'll explain there. So the idea here is, in here, what we have is the idea that types are sets. In here, types are left open. It's a little bit not fixed exactly what types are, or I will say something a little bit more precise than that a little bit later. But here is a fixed commitment that types are sets in a technical sense that I'm going to explain later what I mean by set. And here what we're saying is that types are kinds of spaces, but they're in abstract spaces. And in abstract, they're not necessarily like topological spaces, but they're things that have some characteristics that are like topological spaces. And they exhibit a particular structure, and the structure that has been isolated that is relevant to understanding what's going on here is the structure of a weak infinity groupoid. Okay, and what this is all about, I can better motivate once I give you a little bit more background, because that's what I want to do. Okay, so in order to make some of these statements meaningful, they're just supposed to be teasers. In order to make these statements meaningful, I want to say a little bit about the origins of type theory, which I started to mention here, and that will then allow me to come back and say something so that these little teasers will start to make some sense to you if you don't have any prior experience. Okay, so let's look a little bit at a cartoon version of Brouwer's program. Okay, so as I say, I'm not attempting to run a course here on the philosophy of mathematics. I'm sure you can take such courses in the philosophy department. Okay, but I want to say something about Brouwer's program as I understand it. Let's just say it like that. And it's a working understanding that informs the concept of type theory. And Brouwer's program is based on two main ideas, which, depending on your perspective, can be either trivial or profound at the same time. So one is this, which is that the first one is that mathematics is a human activity or a social activity conducted amongst people. It just means that the process of doing math is about communicating ideas. So the focus is on language for communicating ideas, mathematical ideas. And then Brouwer then analyzed, well, I'll get to that, for communication. Let's just say language for communication of, well, mathematical ideas, mathematical concepts. So you can start out with that principle. That's sort of Brouwer's principle, at least my formulation of it, is, I would say, is blindingly obvious, except that it's not so obvious. There's a lot of people who have other points of view about the nature of mathematics. But I want to take it, it's a social process. And therefore, being a social process, it's fundamentally linguistic. It's all about language, okay, for formulating things. So if it's a social process for communicating, you have to ask, at least some idea of mathematics, which was Brouwer's point of view, you have to ask, how is it possible for people to communicate mathematical ideas? And you kind of have to start somewhere. And Brouwer's point of view is that the fundamental human faculty, the human capability, is the concept of an algorithm. Okay, Brouwer didn't use the term algorithm to my knowledge. I'm not even sure it had been coined at that point. But this was a work he'd done in the early 20th century, first third of the 20th century. And it's based on the concept of an algorithm. The basic premise is that what all people, by virtue of being people, are capable of doing is following a step-by-step procedure. And by giving you a step-by-step procedure for accomplishing something, for executing, for performing, we could say, a construction. And this is where we get the idea that Brouwer's program is also called a program of constructivism. Oh, that should have, I'm speaking and writing two different things at the same time. Forming a construction. So if I want you to construct something with ruler and compass, I say you take a line, you take another line, you drop a perpendicular, you sweep a circle, etc., like the ancient Greeks did. And what have I told you? I've told you an algorithm, okay? And in fact, Brouwer's principle is that the only way that we could ever be talking about infinite things is by virtue of describing how to get at them by an algorithm. That there is no other finite form of communication. That is the only way I could possibly tell you what I'm thinking about. So whether you believe that or not, it doesn't matter, because it's going to, you can argue with this or you could disregard it entirely, but it's historically significant and it completely informs what type theory is. And in fact, I'll get back to that. So the idea is that we can perform an algorithm, and an algorithm is a way of performing a construction, and he harked back to the ancient Greeks, which is some of the earliest mathematics that we know about, okay, that was ever developed. And it's founded on the notion of a construction. And then the radical point, which is extremely central to homotopy type theory, is this one, which is that proofs are forms of construction. And this has some surprising and important consequences. So the notion of a proof in mathematics is nothing other than the notion of an algorithm or a construction. I say to you, assume you have something that you hypothesize, and I say you do this, you do that, you do this other thing, you draw this implication, and voila, you get the conclusion of your theorem. It is nothing other than a program, than an algorithm. Step-by-step procedure for reasoning, but in which the things you're manipulating are proofs. Now, this is where you get the radical departure from every other approach to foundations of mathematics. This is where, regardless if you consider all this BS, there is a technical consequence of this point of view which is unique to type theory, which is the notion of proof relevance. And this is central to the program, and that's the jargony way of saying it. Another way of saying it is that proofs are mathematical objects that we manipulate and conceive just like any other mathematical object. That there's no difference in character between a number, a space, a mapping, a proof are all the same thing. Okay? That's a radical distinction, and I'm going to explain that more technically briefly, because if you look at conventional accounts of foundations of mathematics, which tend to be all the same story over and over, which is basically first order logic with a bunch of axioms, there's no pride of place for the concept of proof. That is, the proofs don't themselves participate in the mathematics. The proofs are off to the side. They're just like the junk we use to write papers. But anyway, they're not mathematical objects. And I want to be careful, because some of you are thinking, who've studied logic, saying, what are you talking about? Think about Gödel and all that kind of thing. No. That is the idea of a formal proof. A formal proof is a mathematical object, but it's only a pale shadow of what a proof is. And that's the content of Gödel's theorem, is that formal proof is a limiting concept, because you draw a line around it. You say, these are all and only the formal proofs right here. You enumerate them. Okay? But what constitutes a proof is, lies well outside of that. And in fact, Gödel gives a proof that a particular formal sentence in here is true, and that proof lives out here and it doesn't live here, and that's the content of the theorem. So you must not confuse formal proof with proof. It's very common to do that, and that's a mistake. Okay, and so that's why I consider it important to stress this point, because I think it's widely misunderstood. So the important thing we're going to draw out of this is the notion of proof-relevant mathematics. And proof relevance is absolutely central. To homotopy type theory. And in particular, we're going to show that we're going to establish some kind of relationship between proofs of equations are going to be somehow related to the notion of homotopies or paths in a space. This is the critical idea. The core of homotopy type theory is exactly to develop this analogy. That's what we're going to do. So they're really going to be proofs. They're going to be proofs in the way that Brouwer formulated what a proof is. There are certain constructions, which means, as I'm going to say in a second, elements of a type. I'll say what that is in a second. Okay, and the proofs of equations are going to turn out to abstract the concept of a path in a space, which is used as a fundamental tool in homotopy theory and algebraic topology, the idea of a path in a space. Now, as a matter of fact, the thing that makes homotopy type theory interesting is the fact that the homotopy theorists never thought of this idea. Okay? This never came up. From the point of view of constructive type theory, it's the most natural thing in the world. And in fact, as a computer scientist, I would wager that all of you as computer scientists with some experience in writing, knowing what beautiful code is, would have invented this if I told you to do it. If I said to you, what we're going to do is we're going to study the concept of path in a space, let's get started, the first thing you would do would be to write down an abstract type. Okay? And you would then give the operations associated with that abstract type and start working from there. That's not what you do in the usual formulation of like homotopy theory. Instead, what you do is you start dropping down to assembly language and you start hacking stuff up, okay, in assembly language. And it's ugly and complicated, okay? But it doesn't need to be. If you do things in the kind of type theoretic style, everything works out beautifully. Not only that, so there's two things we're going to see, is that not only is this idea of proof relevance and the good old computer science functional programming type theoretic way of thinking about the world, about how to write code, not only does it come out to be more beautiful, it's more concise and it's completely mechanizable. So we have a curious situation which I'd like to advertise here. It is not the only situation in which this has occurred, but it's a particular situation in which this has occurred. People have the impression, going back to Russell's Principia Mathematica, or maybe Frege's Grundlagen or Grundgesetze for arithmetic, you have the impression that if you're going to formalize proofs in mathematics, it is going to be the dreariest exercise you have ever undertaken in the entire world, and it's going to be horrible. Okay? This statement is false. Okay? The proofs that we do, like for example in homotopy theory, are cleaner, shorter, more informative, and more general, and completely mechanized than the textbook proofs done by, say, Peter May. So it's not a straw man. Okay? They're better proofs and they're fully mechanized. Okay, this is a remarkable fact. We've seen this also before, like I'm looking at Frank, so I'll think of it, is the stuff we did in logical frameworks and in using 12 to reason about the meta-theory of programming languages. These are the best possible proofs of the meta-theory of programming languages. They are shorter, cleaner, more concise than anything else. If you start doing it inside of like Coq, and you start doing it as conventional mathematics, and I'll explain this, what I mean by that in a minute, it becomes a horrendous mess. Instead, we have, and what is it that I'm hinting at here with both of those examples? What I'm hinting at here is what is called the synthetic perspective in mechanized reasoning. So what I want to think about is this idea of synthetic versus, well, what is called analytic. These two words are used in different ways. Here what I mean this. If you look in the realm, if I put here like geometry, then synthetic geometry is what Euclid did. Triangles, lines, circles, and stuff are things in themselves. They're not sets of points. Okay, they're just things. They're just constructions as they are, and you axiomatize their behavior, and you work from the axiom. Whereas the analytic approach to geometry is sort of, Descartes, the sort of Cartesian view, where you say, well, the geometric figures are sets of points in the plane, and you have R cross R, and you start using the properties of the real numbers. Well, the same thing happens here if I look at homotopy theory. Okay. Homotopy theory, to fit it in here. This is the traditional, this is the traditional formulation of homotopy theory in any textbook that you'll look at. And in particular, when you look at the, what is a path, you say, well, you take the unit interval, so this is contained in the real line. So you take a bit of Euclidean space, and then you map that chunk of Euclidean space into A, and that's called a path. It's a set of points in your space A, in your target space A. And so in order to do this, you have to have around the real line, at least, and then actually you just get various chunks of Euclidean space. So you take the Euclidean spaces as given, and then you start working from there. You're doing analysis, and you're using methods from analysis to understand something about spaces. Whereas in the synthetic approach, it's completely abstract, and this is what is considered in homotopy theory. And this is presaged in the notion of what is called a model category, which is, or Quillen model category, which was one approach to trying to do things more synthetically, but is really done beautifully in Hawk. And if we look at PL theory, it's the same. You can look at something like the synthetic approach looks at like LF or 12. I could look at it like this. You axiomatize the constructs of a type theory using abstract types in a particular systematic way, rather than what you would do, let's say, in Coq. It's been very popularized recently, but I consider it to be like insane, is to try to code everything up down into the primitive notions of set theory. It would be like a difference between, sort of having a parser generator and then using a theorem prover to say that your input S is in L of G, where L of G is defined as a certain set. And then you use automatic theorem proving to prove that your string is in L of G. Okay? It's like completely crazy. Okay? What you want to do is have an algorithm for parsing. Okay? So there's a certain kind of analogy here. So what makes homotopy type theory work is it's doing synthetic homotopy theory as an example of the thing that works out where the fully mechanized concept is much more elegant and beautiful and widely applicable and mechanizable, whereas the other approaches, for example, that you would do the traditional approach to homotopy theory, if I were trying to code this up in type theory, you would expect somewhere in there it's going to look like Bourbaki. You're going to say, oh, okay, a topological space is a triple consisting of this and this and that, and a continuous function is a da-da-da-da-da-da, and it would be like, okay, and about 100 years later we might get the real numbers done, and then we'd be able to say what a path is. Okay? But if you look in the development of homotopy theory in type theory, in Hauth, in the synthetic approach, there is no such definition anywhere. There is no definition of what is a topological space, no definition of what is a continuous function, no definition of the real numbers, or we can do that, but it's like an exercise that we do just for fun, but it's not intrinsic to the way the theory is formulated. I don't have to think of paths as sets of points. Everything is quite beautiful. That's the thing I want to get across. So that happens here. So by way of motivating you for the rest of the semester, I want to sort of indicate this. So it's this idea of the synthetic perspective. So as far as I know, this distinction is due to Laverre. And it's just the idea that type theory is the intrinsic, the idea of homotopy theory is intrinsic to the notion of type theory. So let me explain now what I mean by that. Okay, so that's like a little bit of bragging, because I think one of the beautiful things is how clean it all works, even though it is fully mechanizable. So what I hope we're doing here is completely blowing up the idea, like exploding the idea that mechanized reasoning is inherently tedious and basically undoable in practice. I think that's actually not the case. Okay. All right, so now let me look at here. Okay, good. So, all right. Let me find my bearings here. Find out where I am. Oh yeah, so that's going to come up. Okay, so what is type theory? So type theory is an analysis and codification of Brouwer's intuitionistic mathematics. Brouwer's intuitionism, let's just say it like that. And it draws on a number of crucial ideas that were developed, subsequent to Brouwer's initial inputs. So this was not, an exercise in writing down what Brouwer said somewhere and amplifying it. It's, a lot has gone into this over decades. And one of the important things is bringing in the perspective of proof theory, which I'm going to outline shortly. And in particular, I would say especially drawing on, I'll just write this briefly, Genson's insights into proof theory. So it's curious. I remember 30x years ago, I took a course in logic with Richard Platek, who was a very well-known logician, who said to me, who was taking a class, he said, "Oh, proof theory, the dreariest of subjects." That's what he told me, and I thought, I was appalled, because to me, all the interest in logic is in proof theory, and I thought, I don't know why he thinks it's so dreary, and so part of all of this for me is like a vindication, because I have to admit, because actually, so all of the insights, all of the things that matter that make, for example, in this class, homotopy type theory possible, are based on ideas that were developed in the dreariest of subjects, proof theory. Okay, and so good. So I'll stick my tongue out at Platek, because I don't think he had the right idea, brilliant though he was. So this is where this goes, and the idea is, what you want to do is you want to systematize. What you do is you want to say that there are a notion of type, which type classify what are the admissible forms of construction. That's the whole idea. So the whole organization is that what you do is you say, okay, Brouwer wanted us to base the idea of mathematics on the idea of a construction. And so it's natural to ask, what sorts of things are constructions? And there's no definitive answer to this. It's an ever-evolving notion. People learn more and more what are acceptable notions of construction. But there certainly are quite a range of things that are, have been established and are well accepted. And so that's what the type theory it's a continually evolving subject. Hot is part of the evolution of type theory. But there's some basic principles. And the idea is, which is drawn from Gensen, is to tell you what are the forms of construction. You have what are called introduction rules, which tell you how to create, you might say, for lack of a better word, affect a construction. You could say affect a construction. To affect the construction of a particular kind. And you have what is called the elimination rules, and I'll show this in practice, which is how to deconstruct a construction and how to use a construction in the course of building another one. Okay, so how to use one, so how to create one, maybe how to make one, to introduce one is the terminology. And eliminate, maybe you don't like the word eliminate, but anyway, that's the tradition, which is to the opposite of introduce. You introduce it and then you eliminate it, you take it back apart. And these are linked by what is called the inversion principle. And I'm going to show this now in more detail, the inversion principle, okay, which I also like to call the principle of conservation of proof. Which says that the elim, at the very least, is post-inverse to the intro. At the very least, we certainly have that. So the idea is that you can only take out that which you put in. That's all. So it's like a conservation principle in that you can push stuff around all you want and you can reorganize it in any way you like, but you never get rid of it and you never create anything out of thin air. Okay? So that is the idea. And what these things together tell us is this tells us what are the constructions, and this tells us how they compute. Okay, so the inversion principle is the foundation for the computational or algorithmic aspect, okay, of Brouwer's intuitionism. So in particular, I can also call this the statics of our language. It tells us what sorts of things exist, and this is to do with the dynamics, which is how you run them. Okay, so that's the kind of setup of what type theory is all about. And now the key thing is when you say you classify the notion of constructions, the big thing is it's sufficient to encompass all known, we might say, mathematical activity, or at least that's the programmatically. That is, this is what the intention is. All known mathematical arguments and constructions, in particular forms of proof. So the patterns of proof that we use to communicate with one another are going to emerge as certain forms of construction, and the constructions that we codify and organize into the theory of types will be, the goal is, to be sufficient to do any form of mathematics. Now an interesting thing is going to come up, which is going to require me many rounds of iterative deepening to quell your misgivings. Somewhere in the back of your head you know already that there's something peculiar about this particular notion of constructivism that Brouwer put forward, and that there is bias against it because Hilbert, perhaps the greatest mathematician of the 20th century, quite likely, was vehemently opposed to Brouwer's program of intuitionism because he was mistaken. And that's the part that is not like so widely advertised as the fact that he was opposed. So Hilbert became such a giant in the field that if Hilbert said something, it was true, that's it. Okay, that there was, who was going to oppose Hilbert? Well, Brouwer had the chutzpah to oppose Hilbert, but very few people could do that, okay? And Hilbert was actually wrong about some of the things he said, and but that has given rise to this feeling that there's something deviant or contrary or incompatible between the constructive view and the traditional view that I've hinted at when explaining Brouwer's program. I'm going to attempt to show you through several levels of deepening that that is not the case. Okay? In fact, in a certain sense, it is the type theory we'll develop is completely compatible with classical patterns of reasoning. There is no opposition there at all. Okay? There is no opposition. But it is very important for the purposes of everything I've said so far that the theory be constructive. And the reason is, and so the thing I want to flag on as an aside, okay, so this will come later, is I want to mention here, is the idea that is central is what is called the axiomatic freedom of constructive mathematics. And this is completely central. Hilbert understood, it appears, if you read like the Van Heijenoort compendium of articles about the foundations of mathematics, there are blatant, knockdown, practically bloody arguments between Hilbert and Brouwer on paper there. Hilbert believed that, Brouwer was negating everything that had been done so far, which is not the case. The best way to think about this is that it's just this. Fewer assumptions lead to stronger results. And so what Brouwer emphasized, for reasons that will become clear momentarily, in particular, the infamous law of the excluded middle. The requirement that every proposition is either true or false. Ordinarily, that's taken as a tautology not worth mentioning, but Brouwer he denied it in the sense that he wished to not affirm it. It doesn't mean that Brouwer insisted that the negative is true. That is not the case. That is not what is going on. Okay? What is going on is simply the resistance to affirming this in general. Okay? At the very least, regardless of your foundational commitments and what you may believe, you have to agree with me. If you can prove a theorem with fewer assumptions, you've proved a stronger theorem. Okay? It's better. Okay? That's like not really arguable. Okay? That's like just a better way to go. So Brouwer was insisting that if you work with fewer assumptions, then you're going to get stronger results. And the program of homotopy type theory, exploits heavily this insight of Brouwer's. In particular, if you were to take Hilbert's principle that the law of the excluded middle holds universally for all propositions and types, I'll explain the connection in a second, you would deflate the entire program. Oh, hot ceases to exist. So not only was Hilbert's arguments historically wrong, they were mistaken, but if one were to adopt them on the basis of his authority, you would ruin something extremely beautiful and, I claim, useful. And why do that? Okay? So so just to quell your doubts, some of you may have some doubts because you kind of are already allergic to Brouwer and constructivism because people told you to be. I want to sort of situate that so that you're not so like opposed. Some of that aversion is quelled. And in particular, another consequence here is that we can selectively, what's really important is to be able to selectively, or what I might call locally, introduce handy assumptions. So if you globally introduce the law of the excluded middle, this is in global form, globally, just always, then hot ceases to exist. It's gone. So it can't be done classically. I love this, okay? This is great because it tells us that, you know, it's just the whole idea. If you make fewer assumptions, you get stronger results. You get a richer arena in which to work. But then you can selectively relax those assumptions, or locally relax those assumptions, in order to recover an argument that you may have in mind. You can locally introduce instances of the law of the excluded middle, and I'll show you what are the limitations on doing that and so on, and how you should think about that. But if you just do it with a big hammer, then you've blown your foot off. Boy, that's a mixed metaphor. Okay, you've ruined the whole thing. Okay, so it's a mess. So I find it important to emphasize that the constructivity is central to the entire thing, but it's not a limitation. So this whole business about founding things on the basis of computation, so where does that come from? Okay, yeah. So now that's what I want to motivate next. So Brouwer famously emphasized the non-universal validity, let us say, of the law of the excluded middle. And that created a tremendous amount of friction. Hilbert described it as, you know, you're robbing a boxer of his gloves or something like that. Okay? Words like that. Okay? And but the question you must ask yourself is, why that law? Okay, it's all well and good to, you know, cut down on your assumptions. And if you make fewer assumptions, you're going to get a stronger result. Nobody would argue with that. Okay, but why that one? There's a lot of assumptions you could cut down on. Why not just pick some other random one out of the hat? Well, this has to do with computation, and that's what I'm about to explain. Okay, so it's not, I also want to say, it's not arbitrary which assumptions you deny. Okay. So it's all founded on the notion of construction. And if you think through carefully, what is the idea of a proof, for example, from the perspective of the notion of a construction, then you will be inevitably, irreversibly led to question the universal validity of the law of the excluded middle. And then you are a constructivist. And I know that a lot of people will think, you know, your friends won't talk to you anymore. Okay? But you get used to that. There's nothing you can do. There's nothing you can do about this, okay? The other thing I want to say here, which is very, I guess I should throw this in. Right now I'm emphasizing the aspect, the logic aspect, and that's what I'm going to do right now. That's why I'm preparing the board. But I also want to emphasize the computation aspect, because what type theory is the grand unified theory of computation. It's all about communication, it's all about language, it's all about what programs exist. So it's a bunch of, you could say, comprehension principles, speaking loosely. Okay? They're all about computation. It is what programming languages is. Okay? That's the first thing. There's nothing else. Okay? There is nothing else. We're just studying type theory. So eventually, all the arbitrary programming languages are going to be just swept away with the oceans, and we will have the permanence of constructive intuitionistic type theory as the master theory of computation, without doubt, in my mind. No question. So from my point of view, as a personal statement, working on anything else is a waste of time. Okay, the right thing is put things in terms of type theory. That's the way to think about it. Now I want to say something about that, because it will call to mind the following fallacy, which is, oh, all programming languages are equivalent, aren't they? You know, Church's law and all that. When measured by the number theoretic functions they can encode. That's true. But the whole idea about type theory is it's a theory of computability, and now unfortunately there's a jargon clash, but it's always been called this, computability at higher type. What does it mean to compute with the real numbers? What does it mean to compute with functionals? Things that are not finitely presentable by some encoding as natural numbers. Things that are not given atomically, but must be somehow given in a state of continuous development. So Brouwer had the notion of choice sequence, if you know about this, which was an analysis of what we mean by the continuum. So no program can be presented with a real number in its entirety. Okay? It has to discover what that real number is as it computes. The same is true with higher order functions, functionals, things that take functions as arguments. And one can ask, what does it mean to compute with these objects of higher type? Classical computability theory doesn't deal with it at all. So people who tell you that, oh, it's all just Turing machines, that's flat wrong. Because that's all to do with things that can be written down on a tape in a finite amount. You might as well say written down as numbers. That's all. That's all it's doing. And in particular, it has no notion of composition, has no notion of computation at higher type. So type theory is about enriching and extending the realms of what we mean by computable. And what Homotobi type theory does is extend that to higher dimensional topological objects like the spheres and the toruses. Things like this. This is a whole new, like, terra incognita. We haven't done anything like this before. So the question is, how do we do that? Okay? So that's the big game. That's what type theory is all about. So it's nothing short of a grand unified theory of computation and unified with mathematics. So that there's no difference ultimately there's no difference between the math and the code. That would be my goal. Like, that's what I would like to see have happen. So I guess I want to give you a sense that, I want to give you the sense of the importance of type theory. It occupies a privileged position within computer science. And I just want to stress that. Okay, so now I'm going to start out with some technicalities on a very elementary level. And what I'm going to do is I'm going to begin to explore this idea about type theory from a very basic point of view. And I can't resist drawing my favorite picture here. Many of you have seen me do this before, which is what I call the principle of Trinitarianism and computational Trinitarianism, which is a relationship between type theory, proof theory, or logic, and category theory over here. And there's a complete kind of correspondence amongst all of these subjects. And what I'm going to do right now is I want to say a little bit about the relationship between type theory and proof theory, and also simultaneously a relation between proof theory and category theory. I'm going to explain this a little bit by a very simple and elementary example. So, but in reality, what happens is we go around this triangle all the time and view the same things from the point of view of category theory, from the point of view of proof theory, from the point of view of type theory or programming languages and computation. And as I've said to many of you on different occasions, in my view, what makes something a scientific discovery is in this realm, is you know that it makes sense from all 3 points of view. And if you have a concept that makes sense from all 3 points of view, it's a permanent advance in the human intellect. We've understood something fresh and new, and it's not dependent on the vagaries of the computer industry or any nonsense like that. So that's what I want to do. So what I want to do is start out a little bit with the basics, some basic thing about. I'll start with logic. My point was this. The reason I brought this up is because of the way this works, I can start anywhere I feel like, okay, and then derive the other things from that starting point. But for the hell of it and for a certain reason I have in mind, I'll start with proof theory and thinking about the principles of logic. So let's see how much time I have. I have about 15 minutes, it looks like, right? 49, yeah. So I'll get started. I know that many of you have seen this before, but I think that some of you have not. So, bear with me, there's a reason for it. So let's now start out with what is meant by the idea of intuitionistic logic. And I mentioned this to you before. And I sometimes like to describe intuitionistic logic as if people mattered. And this is really just, oh, it's too bad I erased it. This is really just a a formulation of Brouwer's principle, okay, which is the notion of intuitionistic logic is grounded on the idea that it's a social process, and I'll explain why. So the intuitionistic logic presented in a modern form, this isn't, as far as I know, anything that Brouwer ever wrote down, but it's the type of thing that would make sense to him, is based on what Martin Löf elucidated as the concept of a judgment, and we'll write down a principle. Well, there are two principal judgments. I'm going to do the most elementary case here at the board in order to give you some ideas, which is A is a proposition. So this expresses the idea that A is a proposition. So you can think of this as the grammar. Okay, that just means I've said something well-formed, that it makes even sense to discuss it. And what does it mean to discuss it? It means to judge that it's true, which is A is a true proposition. And now the as people matter part is, which means it has a proof. This is the important idea. So the thing that is significant about Brouwer's analysis is it's a man's eye view of logic and math. That when you write down, when you see a textbook and someone writes theorem, every natural number can be written as a product of primes. I don't know, I just wrote that down for the hell of it. Okay? The person signals, here's your A. This expresses a proposition. In other words, you know what I just said. Okay? It makes sense. It's an English sentence. It asserts something about numbers. You presumably already know what numbers and primes are by the time we get to this theorem. So we expressed a proposition, and we are asserting that it is true. So this is the true part, by saying theorem. And of course, not being bogons, the first thing we do when we assert a theorem like that, we're very quick. You must do it instantly. You say, here's the proof. All right, I won't repeat the proof. And you bracket it. Now, sometimes you say, oh, this is so well known, we don't even bother to prove it. But then it's proved by reference, like in law. We'll say, well, we'll take it as included, as if that document were included here. Okay. So, but essentially what you do is you immediately write down the proof. So in the practice of the social processes of math, you don't ever get to say that something is true without giving a proof. So intuitionistic logic codifies that activity. That's it. Okay? That's what it does. There's no absolute thing. So what does that mean? So you can see immediately now that we do not expect, whoops, assuming, I'm foreshadowing here, that's why I put this in brackets here, that, for example, that either, for any proposition A, we can either prove it or refute it. And I could write that as A false. Let's say, let me just write A false here. Where A false means is refutable. I can exhibit a counterexample. So this means provable. I can give you a proof. Let's say A false means it's refutable. I can give you a refutation. I haven't outlined exactly what I mean by that yet, but you can feel that. We don't expect that everything is either provable or refutable. Why? Because there are open problems. Okay, that's just the fact of life. And there are infinitely many problems and only finitely many of us. So there will always be, okay, open problems. So there's no reason to ever think that every proposition is either provable or refutable. That's obvious once you insist that being true means you know a proof. And I hasten to add, it's not a formal proof. You cannot reason, for example, by analyzing all possible proofs of something, because we don't know what are possible proofs of something in general. Okay? It's an open-ended concept. So that's a terminology that's used, and it's very important, which is the notion of open-endedness. That's a kind of an awkward phrase, but I wish I knew a better way to express, I wish I knew a synonym for that. That sounded nicer, but anyway, open-endedness, a little bit clumsy. Open-endedness is the principle that we do not imagine that we have circumscribed all possible forms of proof and all possible forms of argument, or that all the proofs have been written down in some systematic way and those are the proofs forever and always. We do not make that commitment. If you make that commitment, oh my God, then everything is a mess, okay? So if you try to interpret a true means has a formal proof in a fixed formal system that I give in advance, as soon as you do that, you're wrong. Okay? That's the core of Gödel's argument, right? I cannot start out and tell you, here are all the ways you can prove something, and that's the end of it. Because as soon as I do that, then I can diagonalize out of it. So you're never going to win that game. Okay? So that's what I mean by open-endedness and why I want to distinguish the concept of formal proof from the concept of a proof. In combinatorial theory, I notice that they play fast and loose with the term proof according to convenience. And to my taste, I find it very disturbing because it confuses me. So you have to be careful about how people use the word proof. Okay, so but that's why I'm trying to be careful here. Okay, so now to get something like extremely basic going, let me write down what is called the negative fragment of intuitionistic propositional logic, just a simple thing. Okay, why it's called the negative fragment, I will not bother to explain here. It is what I'm going to say. Let's not worry about why it's called that. Okay, that's a different thing. So what we're going to do is we're just writing down propositional logic. So I'm trying to get the most elementary thing. This would be the kind of thing the thing I like to say at this moment when I give this lecture or lecture on this material is, you know, I don't know about you, but when I was in school, when we took geometry when I was like 14 or something, the first thing we did was learn all the truth tables. And then we started into Euclid, which has basically nothing whatever to do with the truth tables, to be honest. Because the idea of what is a proof, we wrote down in this kind of chart form where you'd write down an assumption, then you would say by this, and you'd write down all the steps. What did that have to do with truth tables? Well, it was never clear to me. So what I'm going to do is write down a grammar of proof, which is the proofs we actually write, without dealing with any kind of things like truth tables, because the truth tables are committed to the idea that there are only two propositions in the world, the trivially true one and the trivially false one. That's it. And the constructive view, propositions have information content, or what we say computational content, and there are many propositions in the world and they don't all get identified merely by the fact that they're provable. That's what's important here. So I don't want to get into the business of like a priori imposing identification, which are completely not necessary. Because, for example, I'll mention, you know, I think pretty much all of the arguments of Euclid are perfectly constructively valid. So the truth table interpretation is definitely not canonical, regardless of what people tell you. Okay, but anyway, all right, so okay, so this is what I want to do. So what we'll do is we'll write down, there are various propositions, and I'll write it like this. This is the trivially true proposition, so we can write it like that. And oh yeah, I want to get down an issue about formal and informal type theory. I'll come back to that next time. What I'm going to do is I'm going to write these down as like formal inference rules because it facilitates my exposition. Later we're going to develop a more informal feel, and we'll get to that. Okay, so we'll just say that's a trivially true proposition, so that's called truth formation or truth F. And the trivially true proposition is trivially true without proof. Okay, you just say it is true because it's the trivially true proposition, and there's no what is called the rule of truth elimination. And the meaning is, remember that elimination is supposed to extract that which you put in. So nothing whatsoever went into the fact that truth is true. It's just trivially true. So of course you can't get anything back out of it. It's the principle of conservation of proof. If you didn't put any information into it, you certainly can't get any information out of it. So that's like the first thing we write down. So the second thing we could write down, and excuse me if you feel this is very boring, but I do have a point, so bear with me, okay? So we'll say, okay, A and B is true. Excuse me, is a proposition is what I wanted to write. If A is a proposition and B is a proposition. Okay, so this is conjunction formation. It can be written like that. Okay, so if I give you any two propositions, I can conjoin them. What makes them a conjunction? Well, what is called the conjunction introduction. And what is the idea? Well, if A is true and also B is true, then their conjunction is true. So that's a straightforward thing. Now, information went into the fact that A and B is true. So I want to then say, if you happen to know by who knows what means that A and B is true, I want to give you a means of extracting the information that went into that fact, which is to conclude that A is true. And then, so this would be, I need a little more space, and let's call it sub 1. And similarly, if you know that A and B is true, then you know that B must be true. Why? Well, it's not because, like, I just flat out say that. It's because these two things fit together. Okay? And I'm not going to get to it in this lecture, but I will next lecture. There's a cancellation principle, which we're going to describe, but it's easier to describe using a little machinery that I don't have available yet, so let me hold that in abeyance. But there's going to be some principle that says this is post-inverse to that. Okay? And then there's a third thing I need for propositional logic for the negative fragment, and it requires a different form of judgment called an entailment. So we'll write it down here. So we'll say if A is a proposition and B is a proposition, and A implies B is a proposition, so that's the formation of the implication. I'm one of these people who writes implication with a horseshoe. Okay? The reasons for that will come out later. And how do we introduce, how do I show that an implication is true? Well, what you do is you assume the antecedent is true, and you deduce from that that the consequent is true. Now, in many traditional treatments of logic, a proper distinction between entailment and implication is not drawn. In the so-called, sorry to say it, in the so-called Hilbert systems, the Hilbert formulations of logic, you suppress this. This is a terrible, terrible, terrible thing that has been foisted on people. So I'm not going to do that. It's very important, and I'll pick up next time in talking about what I mean by entailment. So this is logical entailment, which is the notion, that is prior to implication. And here's what I mean by this idea of being prior. The idea of a mapping between algebraic structures like groups, a group homomorphism, is prior to the idea that in certain situations, such as the abelian groups, you can form a group of homomorphisms. So this is like saying I have a mapping. I have a sort of proof homomorphism, quite literally, from the proofs of A to the proofs of B. And in logic, it so happens that there's a proposition which internalizes such proof homomorphisms as proofs of implications. But in like group theory, like it's not the case for arbitrary groups that the homomorphisms form a group because you don't have any kind of inverse. But if you take the abelian group and you define multiplication pointwise, then you get the right thing. Okay? So that's like a good, simple example. And now let's look at the inversion principle. So the inversion principle says, or the elimination form, if I know that A implies B is true, well, one way to write it is, then we know that A true entails B true. But it turns out to be convenient to uncurry this rule And what we do is we just put that up here as an additional assumption and say if A implies B is true and A is true, then B is true. And that's modus ponens. But what I want to get at is that modus ponens arises not as like some arbitrary axiom that we wrote down, but that it's the inverse to the implication introduction. So next time I'm going to explain more about like what this notion of entailment is, and then I want to connect that up with the algebraic view of logic, the idea of a Heyting algebra or Boolean algebra. So I'll connect this back to like truth tables and stuff in a minute. Okay, I'll get back to that in the next lecture, which is actually the beginnings of the connection to category theory, because Boolean algebras and Heyting algebras are degenerate forms of categorical structure. So that's why I wanted to bring that in. And then I want to criticize that traditional way of treating logic by pointing out the absence of any account of the notion of proof. Then I will introduce the notion of proof. That will give us type theory and its correspondence to category theory. So that's where I'm going to go. And then that's going to give rise to the idea of when are two proofs the same? Lots of people have asked that question. Is that the same proof as that, or is it a different proof? What do you mean by sameness or difference of proofs of a proposition? So what we're going to do is we're going to use that setup that I just sketched to motivate the idea of equality of proofs, one or two proofs the same, which when you run around the triangle will mean when are two mappings equal, or when are two proofs equal, or when are two programs equal. And we're going to use that as a starting point to then talk about a richer notion of type theory, which I will call dependent type theory, which will then get us rolling toward ITT, which now, by everything I've told you so far, will get us rolling toward HOT and etc. Okay, so that's the plan. So at least you know where I'm going. Even if you consider this, you wonder, I'm just telling you. So I have a method to my madness here. So, okay, so I'm going to do this. Okay, so that'll be on Wednesday. I'll pick up. By the way, I woke up in the middle of the night last night realizing I thought I was going to ICFP next week, and it's a good thing because ICFP is actually the week after. So I would have shown up a week early. So the week after next, I will be away. The week of the 23rd, I think that is. Okay, and so we won't have class that week, or possibly I'll force Favonia to do something. I haven't decided. What's that? Oh, he's in Barcelona, so no, I won't even be able to force Favonia to do something. So there'll be no class. There'll be no class that week. Okay? All right. Thanks for your attention.